So hello guys, we are B1 Group 3 from B Division and this is our video explaining the COA topic Division Restoring Algorithm. Next slide. So this is the context page. First we will see the difference between the restoring algorithms, then the flowchart and problems of the two division restoring algorithms, and lastly we will go across the limitations of the division restoring algorithms.
My name is Atharva Vadgozar. My roll number is 18. Coming to the introduction of the restoring division algorithm. The restoring division algorithm uses the method of restoring the binary digits that are stored in the accumulator. Whenever the most significant digit of the binary number stored in the accumulator is 1, then the number stored in the accumulator is taken carry forward and the count is decreased likewise. We will see this in the example. Next slide. So first of all, the zeros are stored in the accumulator and the quotient 1011 is stored. Then we have done the left shift operation and the number is then added to the divisor likewise. So we have seen that the most significant bit of the number stored in the accumulator is 1. So we will carry forward the previous binary digit number that we have stored. This is the principle of the restoring division algorithm. And if the number was 0 in the accumulator or the MSB was the 0, then we would have taken the same 11110 binary number forward in the next count. Second, non-restoring division algorithm. Please take our slide. In in the non-restoring division algorithm, we don't take the binary number stored forward. The carry is not taken forward. The number is as it is taken in the next step. Whenever the most significant bit is 0, then we will see that the number Q naught, or we say it as the least significant bit of the accumulator, is taken as 1. And likewise, if the most significant digit is 1, then it will be taken as 0 in the least significant bit of the accumulator and the number will be taken forward and the carry is decreased. Thank you.
Okay, so next is me. Hello, my name is Hriday, roll number 17 and I'll be explaining the division restoring algorithm flowchart. The restoring division is used to multiply unsigned numbers. The operators used in the algorithm are left shift, subtraction, and carry control using NOT gate. The start symbol indicates the beginning of the flowchart. First, we will take the four registers, initialize the AC register as 0. The divisor will be stored in the M register and the dividend will be stored in the Q register. We initialize the count in the N register where the count depends on the bit size of the dividend or the divisor. Next, we perform the shift left operation on AC, C and Q. Then we perform AC is equal to AC minus M. After that, we ask the question whether the value stored in the carry bit C is 1 or not. This is where we use the NOT gate. If C is equal to 1, we convert the least significant bit, that is Q naught, to 0. This step itself is the restoring step. If C is not equal to 1, we convert the LSB, that is Q naught, to 1. After that, we decrease the count, that is N by 1. In the last, we ask the question whether C is greater than 0 or not. If C is greater than 0, we go to the next iteration. Else, if C is not greater than 0, we end the flowchart. Thank you.
So my name is Harsh Bachav, roll number 14. So as explained by the flowchart by Hriday, we will learn it via an example. So here the dividend is 11 and divisor is 3. Um, so we will perform it as 11 is can be written as 1011. So that's why we will take the value of n as 4 because 11 can be expressed in 4 digit minimum. That's why 4. So always remember if the value is n, the value of m is n plus 1. Similarly, the value of accumulator is n plus 1 and the value of q is equals to n. So We'll perform according to the flowchart. We'll perform the first operation, which is shifting left of A and Q, and then we will subtract A by minus M. So here we will use the 2's complement of M, that is 11101. So we will subtract and we will get our answer, that is 1111011. And since the MSB is 1, we will add, we will put LSB as 0, and we will restore the accumulator which was previously hold. The similar step is followed for the third cycle, but there is something different in second cycle, as the MSB is 0, therefore 1 is added in LSB, that is Q naught, and the restoration of A is does not happen. And the final cycle, we will first shift the entire A and Q to left side. Then we will perform the operation of A equals to A minus M. Here again we will use this 2's complement of M, and at the final we won't restore A and we will add 1 at LSB. So here you can find A, the accumulator, the final accumulator position is our remainder, and the final quotient is our 0011. That is equals to 3, and the remainder is equals to 2. So that's how you perform division restoring algorithm. Thank you.
In divisor, register Q will contain the dividend, and N is used to specify the number of bits in dividend. The second step is we have to check the sign bit of A. Okay. If this bit of register A is 1, then shift the value of AQ through left and perform A equal to A plus M. And if this bit is 0, then shift the value of AQ into left and perform A equal to A minus M. That means in case of 0, the 2's complement of M is added into register A and the result is stored into A. So now step 4 is we again check the sign bit of A. If this bit of register A is 1, then Q0, which is the least significant bit, will become 0. If this bit is 0, then Q0 will become 1. Here Q0 indicates the least significant bit. And the next step is after that the value of n will be decremented. Here n is used as a counter. The next step is if the value of n is equal to 0, then we will go to the next step. Otherwise, we have to again go to the step 2. Next step, we will perform A is equal to A plus M if the sign bit of register A is 1. Then the last step in this, the register A contains the remainder and register Q contains the quotient. Thank you. Next.
So, hello, myself Pranav Achhav, roll number 15. So, now we have just studied the flowchart for non-division restoring algorithm. So, let's work out an example for better understanding of this algorithm. So, starting with, so let's take an example of 10 divided by 3. So, here we denote dividend as Q, which is here 10 and which is represented as 1010 in binary. M is denoted as for divisor, which is here 3, and we denote it as 0011 in binary. The extra 0 in starting, it is just to handle the borrow situation. So now for we will calculate minus M, so which is calculated uh, by finding the for one's complement, and then we add 1 to it. So now as we here are 4 bits, so we will perform 4 cycles to complete. Now we will initialize first C and AC with 0, and we will use dividend as it is. So in first cycle, C0 means it is positive, so we will perform shift right, and then we will perform AC equals to AC minus M, which is shown in the image here. Then we will perform the AC equals to AC minus M, and then For filling this blank space, we will use the NOT gate, so which will convert this 1 into 0, and we will fill the blank space with 0. Next slide. So similarly, we will perform 4 cycles like this. So in second cycle, uh, we perform a shift left, and then we perform AC equals to AC plus M. Here we are doing plus M because our C value is 1, which indicates it's negative. That's why we are performing AC equals to AC plus M. And in third step, we are doing AC equals to AC plus M because it's 1 here also. Next slide. So the last cycle is in last cycle the least significant bit is 0, which means we have to perform first shift left operation, and then we will perform AC equals to AC minus M operation. So here we get the final remainder and quotient here. So the remainder is 00001.
So myself Bhushan Mahesh Bachcha and my roll number is 13. So my topic is limitations and the division restoring method. Also known as the restoring division algorithm is a method for performing division that involves restoring the partial dividend at each iteration. While it is straightforward algorithm, it does have some limitation compared to the other division methods. Here are the few limitations of the division restoring method. Speed, complexity, precision, hardware requirements, complexity in sign division. These are some limitations. So one by one we will see. Speed. The division restoring method can be slower compared to more advanced division algorithms such as the non-restoring division or SRT division. This is because the restoring method requires multiple iteration to complete the division process, involving repeated subtraction and shifting operations. So coming towards the next complexity, the restoring method requires more complex hardware or software implementation compared to the other division algorithms. It involves maintaining and updating multiple registers to store intermediate results, which can increase the complexity of the overall division operation. So next is the precision. The division restoring method may introduce rounding errors or precision loss in the final result. This is particularly true when dividing numbers with a large number of digits or when dealing with fractional divisions. Other division methods, such as Newton-Raphson or Goldsmith algorithm, can provide higher precision in the quotient. Hardware requirements. The restoring method may require additional hardware resources to perform the necessary shifting and subtraction operations. This can make it less suitable for certain embedded systems or applications with limited hardware capabilities. And the last one, complexity in sign division. The storing method becomes more complex when dealing with the sign division, where both the dividend and the divisor can be negative. Additional steps are required to handle the sign of the result and perform the necessary sign adjustment. So, despite these limitations, the division restoring method can still be useful in certain scenarios where simplicity and hardware constraints are not major concerns. It can provide a basic and straightforward approach of division, especially for smaller numbers or situations where precision is not critical. However, for more demanding application, alternative division methods may be preferred. Thank you.